Okay, so we're all happy with that? Did we talk about what part of that is the most important to be looking at? Do not care about the number of protons. We care about the electrons. Because what we're caring about in organic chemistry is bringing two atoms, typically carbon and some other atom, and we bring them near each other and see what happens when they get near each other. What's the first thing that's going to interact between those two atoms? The electrons. Okay. So what we need to know is something about where the electrons exist. So what we've got on the far right here is kind of an energy diagram. Where at this first level we have, I would actually step a little bit away from that. We have the first energy level. Simple as that. So the next one up would be the really creative. Next one. Third. Next one. Actually, I don't care about the next one. Why? I never get there. Okay. Organic chemistry is simple. We pretty much look at the first two rows. We ignore pretty much everything else. Okay. For the most part. Okay. Within each of those energy levels, is that it? We just have one section or one orbital? No. We end up splitting into those individual sections. So we end up getting two different types of orbitals. A lower energy orbital and a higher energy orbital, which we could then name as S and P. Why? I don't know. Somebody thought it was cool. Okay. Actually comes out of the mathematics. That happened to be the symbol that they used for that variable within the mathematical expression. Close enough. Okay. We could then subcategorize those even further, which I'm not sure I quite did. Our S orbital, if we moved into our next concept. So we have our energy level, then we have our orbital type, then what do we have? How did you guys memorize it or learn it? At S and P. We could move up to D. That's fair if we moved into the third energy level. I said ignore the third energy level.
SP like 1, 2.
What do you mean 1, 2, 3?
I think it's depending on what row it's in. It's like 1, 2. I'm not sure.
We have our first energy level. Then we have our orbital types. Then we have number of orbitals. Okay, fair enough.
The number of electrons in each orbital?
Nope. Okay, the way that I've memorized and dealt with it is the orientation.
No, it's the spin.
Not even the spin, because that gets the number of electrons you can fit in an orbital. What does an s orbital look like? A sphere. How many possible orientations are there for a sphere? I take a sphere and I rotate it. Can you tell that I rotated it? So how many rotations or orientations are there? One. How many s orbitals are there? One. When we look at the p orbital, dumbbell, what happens to the p orbital when you rotate it? Can you tell you rotated it? There's your orientations. We end up with 3 possible orientations. And then the fun one to draw, which is
one towards you, one away from you.
one end of that is coming out at you, the other end is going away from you, behind the plane of the board. Okay? So we've got an orbital on the x, y, and z axes. Did it have to be x, y, z that way? Could I have written y, x, z? Why do we specify them as x, y, and z? Okay. Arbitrary notation, deciding how we decide to look at where our reaction is forming, what axis do we want to be on. Once you have specified that orientation, now you got to maintain it. Okay. But it is completely arbitrary to get to that point. So we end up with those 3 possible orientations. We could then start to look at how many electrons we could put in. Well, is there any limitation now on how many electrons we could put in? When you're telling me there's 2, how do you know that 2 fit in? What charge is an electron? Negative. What happens when a negative gets near another negative? It repels. That tells me how many electrons should I be able to put into an orbital. 1. It's not 1. What is it? 2. Why? Our electrons have an opposite spin associated with them. That's how we get 2 electrons per orbital. Okay? That's largely what I want you to get out of your orbital system. We have 1 s orbital, we have 3 p orbitals. Okay? Notice that my p orbitals are located where? I know, big vague question. Second energy level, I'll accept that, but so is the s. Higher than the s. The p orbitals are higher in energy than the s orbitals. Okay. Why? Good question. Let me know when you find out. Big hand wavy answer we could throw in there is a p orbital has a node within it. A node is merely a place where electrons cannot exist. Okay. That is necessarily a higher energy state. The way you could think of it, if there was a place that you could not exist or could not be, what has to happen? Okay. If I told you you could not be in this room, what has to happen? How do I prevent you from being in here?
Shutting the doors.
Filling the room with concrete?
Somebody has to shut the door. Somebody could lock the door. Okay. By not saying that you can't be in here, who has to lock the door?
You do? Right? Anybody?
I said you could be in here. No one should be locking the door, which means no one's getting paid to lock the door, which means it's lower in energy. That node increases the energy. Okay? You can sort of think of it as somebody has to be paid to police that section to keep electrons out. If you are paying somebody to do it, that is necessarily higher in energy. Okay? What happens if we moved up to an even higher energy orbital? What's the next highest energy orbital? D orbitals. What does the D orbital look like? Oh, that was a horrible drawing. Let's try that again. How many nodes are there in the double dumbbell? Higher in energy. Okay. You have 2 planes where you cannot have electrons existing. 2 nodes. The more nodes, higher in energy. Okay. So if we look at our electrons existing in these orbitals, we've now got orbitals, our s and the p. We can look at their shapes. Those are all kind of fun and dandy. We've got 3 possible orientations for our p, 1 possible orientation for our s. Everybody happy with that? Okay. Good, we accept it. Okay. We now look at our periodic table. This will show up on every single exam, plus 1 more little box. Where's that 1 more little box?
Not even what? They talking about going I do it.
You'll see me include iodine on it because iodine is an element that we'll use. That said, or actually, why not show any other element on the periodic table?
We don't care about them.
We don't care about it because it's organic chemistry. This is why organic chemistry is awesome. Gen Chem, you had to deal with the whole freaking thing. How many do you have to deal with here? You're missing a whole section of the periodic table. You don't, 2 sections at minimally. Organic chemistry is even better than that.
Don't get rid of
We get rid of a good, 50% of that mini portion of our periodic table, and we end up kind of sitting happily within that section. Okay? You should know a sizable amount of information about those elements. Okay? What things should you know about them? What patterns do you know from the periodic table already? How many bonds they'll form? That will become important when we actually start putting them together to look at those bonds. We aren't even at bonds yet, but we will come back to that. We could look at the number of electrons in the outermost shell. Again, useful also when it comes back to bonding. Electronegativity. Okay? If you aren't sick of saying the word electronegativity in response to my questions, probably by mid-semester, you probably weren't in lecture. Okay? Electronegativity is your answer to almost everything organic chemistry. Okay? makes up and explains a lot of the observations we see. So you need to know something about electronegativity for each of these elements. Should you memorize the numbers? Probably not, but the trend's pretty helpful. What's your trend? Increases to the upper right. So we are saying fluorine is our most electronegative.
And then it increases from bottom to top.
Okay. And then we would say least, so I'm just going to circle out here, this is our least electronegative. So we increase left to right and we increase bottom to top. What other trends do you know on the periodic table? What about size? This is a tricky one.
Further down it goes.
Further down, absolutely it gets bigger. Why would it get bigger?
Okay, so protons. More protons mean more electrons.
Protons do not determine size.
Different.
The number of electrons. There is a relationship, but if I change the number of protons, I could still get a bigger molecule. Okay? Protons do not determine size. It's the number of electrons. So down a column, absolutely. I'm just going to use one big arrow here. We get bigger. Okay, and we said why? Electrons. Okay. I'm going to hold you there. I'm going to hold you to that answer. What's the trend left to right?
Smaller.
It gets smaller. What happens to the number of electrons as we move from boron to fluorine?
It increases.
It increases. You told me it gets bigger because you have more electrons. And yet we go boron to fluorine. It has more electrons. It doesn't get bigger.
Is it because of electronegativity?
Nope. Related to it, but no.
Electrostatic forces, so the protons are sucking in the electrons more?
There's more protons at the bottom of the periodic table. They should suck in the electrons more regardless.
Oh, because it's in the same orbital. Oh.
That first electron to make boron, or that last one, is in what orbital? 2p. Where's the last electron for fluorine?
Still in 2p. But
It's in the exact same energy level. If it's in the exact same energy level, what happened to its distance from the nucleus? It doesn't change. So when I go left to right on the periodic table, what happens to size?
It stays the same.
Stays the same. Is that true? No, but that's not relevant. Left to right in the periodic table holds constant with respect to size as far as organic chemistry is concerned. Okay? When we look at the size of the atom from boron to fluorine, the atom does not change size significantly enough for us to worry about a size transition left to right on the periodic table. Organic chemistry, already better than Gen Chem. We got rid of 90% of the elements, and we even removed one of those memorization things that you had to do. Other trends.
It's not really a trend, but diatomic seven.
We could look at diatomic molecules. That's again looking at their structure. The issue with our diatomic molecules is they're now locked and they can't react in organic chemistry. So we don't care about those. Pretty sure there's a third one. I don't remember what it was. Oh, orbitals. Kind of goes back to size. So what orbital are we filling? 2p, 2s. Okay? Questions on that? Okay. Functional groups. We got a slide here. Somebody counted and told me 11. So I'm going to trust that. There are 11 functional groups. Are these all the functional groups in organic chemistry? No. Not even close. Okay. Will we see more than these functional groups this year? Probably. These 11 you're responsible for being able to name. Okay. Which is my least favorite subject, and I am working on building some kind of online naming system module that I don't have to worry about at all. And I'll just shovel it all on you to deal with, and then we'll work on it in class. Okay. But I hate talking about nomenclature. Okay. So you need to be able to go through and name these by the end of the year, and that being the full year of chemistry, or organic chemistry, so both semesters. Okay. For first semester, our primary focus, I've got a weird echo over here. I'm going to step away from that. We need alcohols, alkanes. We need this whole first column. We'll probably name our alcohols and ethers, okay, as our primary focus. The rest of them are kind of relegated to second semester material. For those of you not taking second semester at all, you don't care. For those of you taking second semester with somebody else, you will be learning those nomenclature then. Okay? If you're taking it with me, you will learn the basics of all nomenclature this semester, but I won't test you on those other ones.
Do you teach second semester?
I do teach second semester.
Does it
In
transfer?
spring.
Do you do it, yeah, do you do it during summer?
I do not teach it during the summer. I think that's an awful, awful idea. For those of you trying to take organic chemistry during the summer, second semester is the best one to take. First semester is a horrible idea because too much of it you need for second semester. Okay. Second semester you can kind of brute force memorize your way through it. Don't recommend it, mainly because I'd rather have you be in my class, but that's kind of neither here nor there. Okay?
You do teach it in the fall, right?
I do teach it in the fall. Okay. Other questions? Let's move forward. Atoms to compounds. So we take two atoms, we bring them near each other, and we see something happen. What do we see happen?
The electrons interact.
Okay, the electrons interact. Okay. Just going to bring the next question. How do they interact?
Repel from each other.
Okay. They repel from each other. Do you have a different idea?
Yeah, or one shares, they share each other's electrons?
When we bring those two atoms near each other, we do have the possibility of those electrons encountering each other. In which case, the electrons meet up and say, hell no, and they repel away. But what happens if they're slightly askew and that electron doesn't immediately see that electron? If they're close enough to interact with each other, they're also close enough to interact with the other atom's nucleus. What does that mean happens with those electrons? They're being pulled between two different atoms or two different nuclei. So how would we describe those electrons? Would they be owned by any individual atom? They are shared between two atoms. And what do we define as a shared pair of electrons? A covalent bond. So we have two possible options. Every time we bring two atoms near each other, we get a repulsive force where the electrons do not occupy the space between the atoms. In which case, what do we have? That's a hard question. Come up with a name for it. Inert. It's good enough. What happens if the electrons do exist between the atoms? We have a bond. So every time we bring our atoms to each other, we end up with either a bond or inert. Okay, we'll come up with a slightly less creative name than inert in a little bit. Okay, so we've got two possible interactions. What things are going to control those interactions? Electronegativity, size, okay, where the orbitals are located. Okay, how do those electrons interact with each other? Okay. So if we go through and look at those, we end up with kind of a broader spectrum off of those interactions. The electrons can either be shared entirely, or maybe they're just loosely shared. Okay? So we can look at that stronger interaction where they're actually getting some direct involvement with each other as either a full-on bond, or we can say they're really sharing electrons, but the electron from one sees the nucleus of the other, it's not willing to jump. But that is still an attraction between them. But I can't call that a bond anymore. What should I call that? Whoops. Never mind. We'll ignore that. I thought I was somewhere else. So, we end up with either our repulsion, not a bond, okay, which was our inert option, or a bond. That's how we're classifying it, at least initially. A strong attraction between them, or no attraction between them. Those are our two options. Do we have possible variations off of that? Yeah. We could run into a system here of entirely not a bond. Well, if they're not a bond, there's no interaction. It's kind of hard to say we have variations of not an interaction. But when we move over to the attraction, can we have varying levels of attraction? Yes. As you might have guessed by cheating, my fault, and looking at the next slide, we can look at various types of bonds. What are the three bond types that you already know? And I already gave you some of the answers. Ionic is a bond type. Covalent is a bond type. Hydrogen bonding is not a bond type. Van der Waals is not a bond type. Polar covalent is a bond type. So that's interesting. Maybe we should change covalent. Non-polar covalent. There are three bond types. Are there other interactions that are possible? Yes. Hydrogen bonding, London dispersion. All of those are favorable interactions. In fact, they have varying strengths of attractions, but they are not defined as bonds. Okay? So when we look at it, we've got three possible bond types that you are responsible for. So let's pick some examples here. Let's go with, let's do, that's too hard. Let's go with CC. Let's do a little CO, and let's do CMG. CC, which type of bond? Non-polar covalent, I agree. CMG, ionic, I agree. CO. Okay. I'll kind of accept that, and I got one which is nice. There's one change, we'll make it CH. What type? What do you think I'm trying to get at here? Varying degrees of each of these interactions. Fair enough. Okay. When we're looking at that attraction, we establish cut lines. Okay? And we say, well, if it's this, it is this type of bond. If it is this, it is this type of bond. When you look at the rainbow, what colors were you told to memorize in the rainbow? Roy G. Biv. Is magenta in the rainbow? Yeah, it is. Because the rainbow has the entire spectrum of all colors. How come there's no M, right, in Roy G. Biv? They don't want to list all of the colors. Exactly right. When we're looking at our bond type of interactions and ultimately our forces, which we'll get to as well, these are arbitrary lines that we put on a spectrum of possible interactions. We look at a rainbow of interactions. Within that rainbow, we said we see red, orange, yellow, green, blue, indigo, violet. When we look at the spectrum of interactions that we've classified as bonds, we see ionic, polar covalent, non-polar covalent. Okay? We have gray areas within that. But we use those major classifications because those classifications allow us to predict other things. Okay? Which brings up the next question. How do you know that those particular bonds belong in those particular categories? How did you match those up? Okay, we got two good answers, or at least I think I know where you're going with your answer. Electronegativity, absolutely the end-all be-all answer for all things defined with bonds. What was the electronegativity of carbon? 2 point something was more or less the same correctness as 2.2 and 2.4. It's 2.5. What is the electronegativity of magnesium? That's what I thought. You didn't memorize your electronegativities, So telling me definitions of each of these bond classes based on electronegativity is a horrible idea. Is it correct? Yes. Not useful. We need something else. What was your suggestion on ionic?
For ionic, you can usually always tell because it's, you have the metallic and non-metallic.
Yep. Metal and a nonmetal. Easiest way to get through it, this is the way that you should be approaching all ionic bonds. You see a metal and a nonmetal, it's an ionic bond. Immediately jump to it, there's your answer. Okay. Polar covalent and nonpolar covalent. We're going to run into an issue with those two. Our ionic, we said, was metal, nonmetal. Cool, we got that. Look at that, I even color matched. Okay. Thank you for laughing, I appreciate that. Carbon to hydrogen, you said was nonpolar covalent. There was a little bit of wishy-washiness there, but you were correct. It is nonpolar covalent. Is there a metal there? No. Oh, so maybe my definition for nonpolar covalent is nonmetal, nonmetal. There's a reason I'm not writing that. The carbon to oxygen bond for our polar covalent bond is also two nonmetals. So defining our covalent bond based on nonmetal characteristics is useless again, just as bad as our electronegativity. We need something else. Ideas? I know one of you, or three of you have ideas on this. But you don't have to volunteer, it's okay.
Dipole moments.
Most people jumped all over carbon to carbon being nonpolar covalent. There was very little question in that. That was my general feel out of that. Is that good? Okay. Why did you say carbon to carbon? Same electronegativity. Which means we have equal sharing of electrons. Okay. Again, both those definitions are pretty useless to us because how do we define equal sharing of electrons without using electronegativity? But what we could use for our nonpolar covalent is same element to same element. That works. That covers our carbon-carbon bond. Does not cover our carbon-hydrogen being different from our carbon-oxygen. So we need another rule.
Is it the number of electrons in the outermost shell?
Unfortunately not.
There's a difference of electronegativity.
If you go back to difference of electronegativity, you will absolutely be right, but you have to memorize the electronegativities. It's kind of a dumb one. You ready for it? It'll be a bit anticlimactic. Anything bound to itself and carbon to hydrogen is nonpolar covalent. So then what is polar covalent?
Anything bonded to itself is nonpolar covalent.
Anything bonded to, so of that same type of element. Same to same is easier to say. Everything else. Okay. So look at your bond. Is it ionic? No. Is it nonpolar covalent? No. What does that mean? It's polar covalent. Periodic table has a ton of different elements with a ton of different electronegativities that can mess that up to all sorts of yin-yang. Thankfully, we aren't looking at the entire periodic table. We're only looking at those 10 elements that we condensed our periodic table down to. And when we look at those 10 elements, they fit beautifully within these rules of thumb. Okay? Extremely helpful to be able to look at a molecule and classify that bond, because that gives you information about its reactivity. Okay? Question? Okay. And I didn't cut any paper slips. Oh well. So I'll just pretend you were all here and give you full credit for it. Quiz technically number 3. Okay? What I want you to do is spend no more than 5 minutes. What I want you to do is actually ignore providing the Lewis structure. I don't want you to give me the Lewis structure for SO4. If you need to, for your own sake, that's fine. But what I want you to do is write down on a blank piece of paper the steps or the rules necessary to draw the Lewis structure for SO4 minus 2. Give me those rules. They do not have to be right. They do not have to be correct. But do whatever you can to give me the rules to draw the sulfate ion. And if you have questions about that, raise your hand.
You're gonna collect this.
Ideally, don't talk to people around you because that's going to be the next part of it. I'm going to draw up a couple structures here. Should not be recording. So you need to show the dots. Second one. Unless I made a counting mistake, that should be fine. That has the correct number of electrons.
You need to show the -2 a different way.
It's actually fine. Last one. So there's an interesting question. Too many bonds on the sulfur. Some of you have connection to the internet, and I noticed, I appreciate it, that you did not look up the Lewis structure for sulfate. How about you do that now? For those of you that have access to the internet, do it real quickly. What does the internet tell you?
Got the one on the right is the right.
The internet tells you the one on the right is the correct one. And that middle one, I would argue we can do a little bit better than that, so I'll actually clean that up a little bit. That middle one, we can make it better, maybe getting a little bit more specific with it.
It does show the middle one though.
The middle one does show up with all those charges. Oh, good job, internet.
With the brackets too.
Okay.
Both show up, but
All answers are technically incorrect. Okay. Which may be an exceedingly frustrating concept because you use the internet and the internet never fails you. This is what's fun with Lewis structures and what's kind of unfortunate with it. The concept that the internet is not showing that is important in this aspect is something known as resonance. Okay. Resonance is the ability to move electrons in pi systems, which we haven't officially talked about yet, so let's call it in multi-bond systems, for lack of a better descriptor, to different multi-bond locations. Okay. If we have the ability to move those electrons around and we form an equal energy structure, we are responsible for showing each and every single one of those structures. In the case of sulfate, it sucks, so I'm not going to do it. Okay. There's a lot of them that you should technically be drawing. Both of these structures technically cover all of the rules that you've been introduced to in general chemistry. The one extra aspect that general chemistry did not really either push or emphasize is number one, resonance. Okay. You see very few examples of it discussed, and they're very limited in their context. And number two, what makes a good Lewis structure? The one on the right is a better Lewis structure than the one in the middle. Okay? And it is for what is effectively a completely arbitrary reason. That arbitrary reason is there's a lot of charge shown in the middle one. The far right has shown a minimization of that charge. But as someone addressed a little bit earlier, at what cost did it take to remove that charge? We broke the octet rule. Well, why do we have the octet rule if we can break it?
You want to break it for certain elements, right?
to minimize the electronegativity of the.
Why are we breaking it for certain elements?
Is it because there's actually a d orbital on that sulfur?
Why are we ignoring the d elements when we came up with the octet rule? Lewis built this theory to explain simple bonding. Simple bonding explains or is explained by the first two rows of the periodic table because there's only two possible orbitals that we can work with. As soon as we move to that third row, we're now at a third energy level and we have three orbitals to work with, three orbital types. Because we now have three orbital types, what happens to the level of bonding? It becomes more complex. Within that increased complexity, you can see an exceeding of the octet. Sulfur, being in the third row of the periodic table, has access to the d orbitals. Oxygen is not in the third row. It can never exceed the octet. Why did the initial theory not evaluate those third rows? Or third, fourth, fifth, 90% of the periodic table? Because it was too hard. Start simple, make it more difficult as you have to, but keep it simple first. So when we're looking at our Lewis rules, we can exceed the octet, but only in certain circumstances. Okay? When we look at these two structures, depending on who taught you Lewis structure, you'll come to different answers. You may have been taught the one in the middle is fine. Okay? It kind of, sort of is, because it does represent a correct representation of sulfate, but it doesn't correctly represent Lewis structure rules. So what are the rules that you should be following? How many of you actually had legitimate rules that you were like, yeah, when you guys teamed up and said, okay, my rules are the best, you followed their rules to the letter and you got one of those answers? Any table? No tables. You wrote down rules, didn't you?
Yeah.
But you didn't follow them? What did you do?
Well, I wrote that, and then I made the rules based on what I wrote.
You knew the answer and tried to make rules based off of your answer. Okay? We do that fairly frequently in organic chemistry. It's called the lab. We go to the lab, verified it, and then went back and made up some rules to match it. Okay? You have to be careful when you go through and approach these questions to make sure that you're doing it at the proper time. Okay? When it comes to Lewis structures, I am nasty nitpicky about this. These are the rules. Okay? Nobody else's rules are good. I wrote these rules. They work every single time. Okay? There's a lot of rules on there, but it works. It's beautiful. It does awesome things. Okay? For simple structures. And what you'll find when you're in organic chemistry, when it comes to building structures, and particularly Lewis structures, is that we throw tons of questions at you and say, draw 50 carbon compounds. Draw 50 nitrogen compounds. Draw 50 oxygen compounds. Now draw 50 where they're mixed. Okay? The only reason we have you go through and do all that is to come up with the patterns, the commonalities that was suggested earlier in finding the periodic table, the number of bonds each element can have. Because once we know those patterns, we just mimic those patterns and we ignore the rules. Which is effectively what you did. You drew the structure of sulfate because you knew what it was supposed to be, or thought you did, and went back and made some rules around it. These rules will allow you to find arguably the hardest part of organic chemistry, resonance. If you start drawing multiple bonds right out of the gate, you've already lost your opportunity to be able to find resonance easily. What you need to do is come naturally to the conclusion of resonance. After that, your last step, which depending on what class you're in, I didn't write down the rules there, assigning formal charge to each and every atom. Some instructors insist you do this, some do not. You need to be able to do it now. Okay? Your formula, because it is a calculation. There wasn't a lot of math there. I said there was no math. There is some math. Your calculation for determining formal charge, relatively straightforward. And depending on the textbook, general chemistry textbooks love units, so they tend to be really specific with their units. Your formal charge is equal to the number of valence electrons on your atom minus the number of non-bonding electrons minus,
Is that non-bonded pairs or just non-bonded?
come back to that. What was that? 1/2 the number of electrons in bonds. How many electrons are in a single bond? 2. What is 1/2 of 2? 1. What if you just counted the number of bonds? Yeah, it works. Why do they tell you 1/2 the number of electrons in bonds? The unit is? The unit is? What's the goal of 151 and 152, despite what any general chemist tells you? Units. That's all they do. That's it. Okay? Get beyond the units to the meaning. The meaning is trying to figure out your balance of where the electrons exist minus the number of bonds. And you have your answer. Don't give me this nonsense that the units don't match. I don't care. Okay? This gets you the correct answer without making it unnecessarily convoluted. Okay? We are going to start Wednesday with these examples. Okay? And by starting Wednesday with these examples, what I expect is that you have done these examples, and that when you walk into class in your little groups, you will decide, what do we got? 7 tables, something like that? You will decide which of those you want to draw on the board, and you will draw it on the board. The last group in here, or the last group prepared to write an answer on the board, will probably have to draw the hardest one. So if you get here early, you can draw your easiest answer up there right away. I expect all valid Lewis structures, which will get nasty. But that's what I want you to go through and do.
The last one?